So, welcome back friends. So, we were doing simple process using Green's functions methods, and from the Green's functions methods we derived this bunch of relations, rules which we called it as Feynman rules essentially. I did not show you the complete formalism because it is a little bit involved, but the methodology is very simple compared to in the same fashion as the one which we has used in the Green's functions for calculate a general Green's function for solving a wave function in the presence of interactions, like in time dependent perturbation theory, like what we have seen here, that in perturbation you keep adding and the Green's function keeps adding up essentially, and the new Green's function is the corrected in terms of the original Green's function times the corrected Green's function accordingly essentially. So, you can keep adding these Green's functions with an interaction at that particular point essentially. So, the total Green's function, how do you solve it perturbatively is with interactions essentially, with interactions is step by step and in this same fashion. So, we are using Green's functions methods essentially. So, then we derive this bunch of rules for the scalar QED, or what do you call as pion electrodynamics, and then here we said we will only take the leading order corrections as leading order interaction terms. So, we neglected this particular term at least for process at the leading order. We will come to next leading order in a second essentially in coming lectures, not in a second, but anyway. And then again we emphasize that what is what, remember that we are going to treat the wave functions to be free particle wave functions, but the interaction will exactly like in perturbation theory, the interactions would be multiplying with the free particle wave functions. Now, in this particular case, which is curious, essentially you have a momentum dependence in this particular case because there is a del mu sitting here. So, del mu gives you momentum of the pi 1 and phi 2, which is the incoming pions essentially. So, the strength of the coefficient of the product of these three wave functions is given by IE, not just the strength of the coupling constant which is E, but also P2 minus P1 essentially. It is also a momentum dependent coupling constant essentially. So, it is no longer a constant in real sense, but it is momentum dependent at the tree level itself. At the tree level itself it is momentum dependent. That means at the leading order itself it is momentum dependent. So, I am calling it as the simplest example, but it is a little bit involved compared to the other cases essentially. So, the particle is represented with the incoming wave essentially like this, and an antiparticle is represented by opposite direction wave line like this essentially with the charged sign reversed. The same thing with outgoing will be particle in this particular fashion and the antiparticle. Now, here we can multiply the spinors if it is a fermion, or you just multiply with ones essentially if it is a scalar, because the scalar does not have any spinors except the plane wave part. All the plane wave part adds up to give you something, what I will tell you, adds up to give you this particular phase factor. All the plane wave part gives you to give you this phase factor of the wave function. So, you for the present you do not consider the plane wave part, and the plane wave part is added into the matrix, into the total cross section in terms of the phase part essentially, in terms of the phase part. Okay. So, now you, because now you, and then there are the propagator wave functions or propagator wave functions which are nothing but momentum space for in momentum space given in terms of eta mu nu by q square for the photon, which is represented in this particular fashion. Remember, the propagator has two dots on both sides and I by k square minus m square for the scalar propagator or the Klein-Gordon propagator. There is an I epsilon, remember that I am neglecting it for the present. Okay, there is an I epsilon always essentially, which you have to keep in mind. Now, we go further and then we considering a 2 to 2 process essentially, and then I said there could be exchanges of momenta, all possible exchanges of momenta. The first one is in which the two incoming momenta can add up, giving you the particular the final momenta, essentially the exchanged momenta, which is called the S channel essentially, which is also called the S parameter, which are all the three of them go into the name of Mandelstam variables. The second one is P3 minus P1, one outgoing, 2 with 1 incoming. Essentially I think I made a mistake in the previous lecture saying that it is P2 minus P1 in the notation, but it is P3 minus P1 whole square, that is equivalent to P4 minus P2 whole square, because okay, the incoming the time direction is here in this direction, and the opposite, which is P4 minus P1, is called the U channel. It is called the U channel. These three are the three Mandelstam variables. Now in the limit all the masses are same, if they are all equiparticles, essentially all the 2 to 2 scatterings are all of them are the same particles, say all of them are electrons or something essentially, okay, then this just becomes 4m square essentially, S plus T plus U just becomes 4m square. Okay, these are all the same particles, say they are same particles. So the scattering amplitude is also called the matrix element, essentially the matrix element is defined by Im. So a matrix element Im. So and the Feynman rules which we derived or which we wrote down, we did not actually derive but we wrote down in the previous case, in the previous what do you call, in the previous slides essentially, the Feynman lectures, Feynman rules end up defining your scattering amplitude, okay, the matrix element essentially Im, and the cross section is given by mod m square times phase space factor essentially, phase total. So this matrix element is giving you the scattering amplitude, and the total cross section is nothing but mod m square times the phase space factor. Now here I written in terms of 4m, this is coming from the plane wave functions sitting in the calculation of the amplitude. Now this I have written it in as though that I have written it in terms of 4 component form essentially, 4 component momenta essentially, but you can write it in terms of E1 E2 and P1 P2, and this is sometimes could become non-trivial for higher number of particles essentially. Now the integrals can be solved, the phase space integrals for 2 to 2 process are simple, for a decays it could be, it depends upon 1 to 3 or 1 to 4, for 1 to 3, 1 to 2 they are easy to solve, and from 1 to 3 onwards they are slightly difficult to solve essentially the phase space integrals. All this particular fashion comes under relativistic kinematics, and this is sort of independent of the interaction strength or anything essentially. The phase space factor is independent of the interaction strength essentially, it is, that is the reason why we decouple it into 2 parts, whereas the phase space is independent, it only depends on the masses, energy, and only the kinematic factors, which is essentially the relativistic kinematic part, and m square is the one which is sensitive to the interactions, which is sensitive what kind of interactions you have and so on, so essentially. Okay. So but these phase space factors can be calculated by known methods essentially. These are calculated for 2 body process and for 3 body process and everything, and the general n body also. There are general formulations given in terms of some integrals. Some of these integrals are hard to solve depending upon the number of particles, final state particles. But anyway, this is a different thing independent of the interaction. Since we are dealing with interactions and relativistic kinematics essentially, we are not dealing with relativistic kinematics, but it should be dealt at some point essentially. Either you can self study or you can refer to these reviews and everything. Okay, I will try to cover some of them in the coming lectures essentially. Due to lack of time I will not be able to do everything. So I will only focus on how to calculate m. Okay. So to calculate m, what I will do is I will consider the process at hand essentially, which is pion scattering. So I will try to draw all possible scattering cross section channel, which are the all possible S channel process or T channel, all possible channel process which are allowed in this particular case, essentially in this particular scattering process, in this particular scattering. In this particular scattering process, I see that first of all, if you take time in the horizontal direction, there could be an S channel process in which the pions annihilate and form a virtual photon and then decay into again pi plus pi minus. Okay. This is a virtual photon, this is a propagator. The pions come in, virtually annihilate to form a virtual photon, and they annihilate and to give you 2 photons. In fact, you should be careful if they really annihilate, if instead of they form actually 2 photons essentially. Pi plus pi minus always forms 2 photons, okay, they form 2 photons essentially. Okay, there are theorems for it and everything essentially. Because of various conservation laws and everything, any annihilation E plus E minus particle antiparticle always gives you 2 photons essentially. Okay, you cannot have single photon. Okay, but if because it is not on shell, this photon is not on shell, this is off shell, you are allowing a single photon essentially. You are allowing a single photon. Okay, if it is a not a virtual process, this is not an exchange, then this will give you pi minus pi minus. Now the second diagram, is there any other diagram allowed, and this diagram is this particular thing essentially, pi plus pi minus and everything. Okay, this is also the other diagram essentially. So this is a, now in the last lecture before I closed down, I said that is there a U channel diagram possible, essentially I left it as a question, as an open question, and okay, I could not solicit your answers because you could not have an online quiz and everything essentially. But let us just say, is there a U channel process? Now if you try to draw a U channel process, what will happen? Essentially let us try to draw a U channel process. So this diagram, the way I calculate is I start with what is the incoming wave function, the vertex outgoing wave function, then the propagator, then in outgoing wave function, vertex income outgoing wave function 2. So IM is equal to incoming wave function one times vertex times incoming wave function 2 times propagator outgoing wave function 1 times vertex outgoing wave function 2. So this gives me, I can directly write down the vertices because I know the vertex. So the wave functions are 1 unity because I do not care, because I consider 1. The vertex is P1 minus P2 mu, and then the propagator 1 by P1 plus P2 whole square, because it is nothing, and then the outgoing wave function is P3, outgoing thing is vertex is P3 minus P4 mu. So here you have your first amplitude, which is simple in structure, it only has momenta, it does not have any spinors or something, it only depends on the momenta P1, P4, P3, and then there is, this is your IM. Okay, this is your IM. So there is nothing, there is just a vertex, propagator, vertex, outgoing wave function and so on. Okay. This is your first amplitude which you have calculated, and you can do the similar amplitudes for all this process one by one essentially. So, given this process, now you can compute the m square by taking the mod of this okay, calculate the mod of this essentially, and then you can get the amplitude in terms of the momentum. And now you know what is P1, P2, P3, P4, you know what is the differences, and then you can calculate, and then you also have the cross section given by I mod m square times the phase space vector. Okay, I mod m square given by the. So, this gives you the correct things. It does not give you any what do you call things like Zetter-Bitter-Wiegang, Klein paradox or something. It gives you correct answers. Okay, verified by experiments. So, this gives you okay correct answers which are verified by experiments. Now, this process is validated for you. Okay, this process is validated for you in terms of your experiments and everything and your calculations, and it is consistent theoretically also. What happens is it does not lead you to problems in like Zetter-Bitter-Wiegang or anything, but the difference is that okay. Now, the point is that now you can ask the question that how do you define how do you now here we did not use any quantum field theory, we are just using wave functions which we had defined and everything, multiplying it and calculating this thing. Now, how do you go to higher orders is the thing which we had to still address essentially. Now, the point is that if your experiment becomes precise, how do you go to higher orders is the question we still have to address. Before going to this thing addressing this problem, now you realize that there are issues in this method also. There are issues which are bigger problems. I am claiming that this method works very well, this is perfect and everything, but as we will see, because there are issues this method which will lead to problems, because we are using wave functions which are not fully wave functions which are free particle solutions, and we are using perturbation theory, and this inherently creates some problems with virtual particles. Okay. But before doing that, what we will do is we will use in the next lectures we will do the same analysis with Dirac field theory essentially. Okay. We will derive the Dirac propagator and do Dirac electrodynamics and start doing this process one by one, okay, and try to calculate simple amplitude process, and then we will see if there are any issues in higher order correlations. But before that, I will also want to introduce you the Dirac propagator first, and then we will continue addressing more issues and why this method is very good, because most of the particle physicists, if you take any particle physics book or any of the simplest field theory books or something, for the tree level process this works very well. There is whatever I have told you, you do not need anything. If you want to calculate simple cross sections, essentially E plus E minus Baba scattering or photon Compton scattering or any of these things, we can calculate this thing very simply essentially. Okay. We will see this 4 or 5 fundamental process and everything, but what we will see is that if you go to higher order corrections, you need more process of renormalization and everything. and this becomes complicated while we understand the qualitative picture. To deal with in terms of wave functions becomes formally impossible, formally it does not make very sense. So, it is better to move to a quantum field theory, but as far as practicality is concerned, this is exactly what we do in quantum field theory also. This is how you calculate cross sections, this is how at the tree level, this is how you do everything, but the interpretation of what is a wave function becomes problematic in a relativistic setting, which as we will see in the coming lectures essentially. Okay, I will stop here and I will continue again. Okay, thank you very much.